Swayam Prabha. Digital India. Educated India.
Good afternoon. Welcome to this course on acoustics. In the last lecture, we had touched upon the area of Bode plots, pole zero plots, and phase and magnitude plots for transfer functions in the context of providing the students or people who are interested in learning about acoustics some grounding in some of the basic concepts which will be quite often used later in the course of acoustics. So, with that intention, in the last class I had covered in somewhat detail on the concept of Bode plots and specifically I had developed Bode plots for magnitude and Bode plots for phase for complex zero functions and for simple for transfer functions which include simple zeros or for transfer functions which include just simple poles. So, today we will use all that information which we talked about in the last class and we will go a step further. We will start with a transfer function which will have which will be essentially a combination of poles and zeros, and for this transfer function we will construct a Bode magnitude plot and a Bode phase plot. So, in this context, let us say that the transfer function for which we are interested in developing a Bode plot for magnitude and phase, it looks like this s plus 2 over s square plus 6 s plus 25. Okay. So, if I find the roots of the denominator, essentially what I get is in the numerator I still have s plus 2 and in the denominator I have s minus 3 plus 4 j times s minus 3 minus 4 j. Now, remember that these Bode plots are for the case that s equals j omega. So, in this transfer function I replace every s by a j omega. So, what I get is h of j omega is 2 plus j omega in the numerator, and in the denominator I have minus 3 plus 4 plus 4 plus omega times j. This is one linear factor of the denominator and the other linear factor is minus 3 plus omega minus 4 j. So, this transfer function is essentially a product of three individual functions, transfer functions, which is h 1 j omega times h 2 j omega times h 3 of j omega, where h 1 j omega is 2 plus j omega, h 2 of j omega is 1 over minus 3 plus 4 plus omega times j, and h 3 j omega is minus 3 plus omega minus 4 times j. So, H1 is 1 over minus 3 plus 4 plus omega times j, and this is the expression for H3. Now, as we are trying to develop a Bode plot for magnitude and a Bode plot for this transfer function, what we will do is first, so let us start by just thinking about the magnitude part. So, we will construct a Bode plot for magnitude for H1, we will construct same thing for H2 and the same thing for H3. And then, because these Bode plots are essentially, especially the magnitude is a logarithmic function, because on the vertical axis we are plotting decibels, all we have to do is add up these 3 Bode plots and we will get the final Bode plot for magnitude for the original function, which is h. So, that is what we are going to do now. So, now what we are going to do is we are going to construct for a Bode magnitude plot for H1. So, once again that is my original function. As omega is approaching 0, when omega becomes extremely small, H1 j omega approaches to H1 j omega. So, in decibels this approaches 20 log of to the in base 10 of the number 2, which is essentially 6.02 decibels. Similarly, as omega is approaching infinity, H1 of j omega approaches j omega. So, if I am going to calculate the strength of H1 in terms of decibels, that approaches 20 logarithm in base 10 of omega, because the magnitude of j omega is omega. So, these are the 2 asymptotes. Once again, this is the low frequency, the first one is low frequency asymptote and the second one is the high frequency asymptote. So, for H1 the Bode magnitude plot is going to look something like this. Bode magnitude plot for H1. So, on the horizontal axis I am plotting logarithm of omega, and again it is logarithm on base 10, and on vertical axis I am plotting decibels. I know that my low frequency asymptote is a horizontal line, it is a horizontal line which cuts the y axis at 6.02 decibels. Also, I know the crossover point is such that when omega becomes 2, then the high frequency, then after that the high frequency asymptote becomes more important. So, my crossover point, this is my crossover point, and that is essentially log in base 10 of 2, and my high frequency asymptote is a positively sloped line, the slope being 20 decibels per decade, 20 decibels per decade. So, I have, this is my high frequency asymptote, this is my high frequency asymptote, and this is my low frequency asymptote. So, this is my Bode magnitude plot for H1 of j omega. Likewise, now I am going to construct a Bode magnitude plot for H2 and H3 functions. We will rewrite the relation for H2, and that is 1 over minus 3 plus 4 plus omega times j. So, that is H2. As omega approaches 0. So, now again we are trying to construct a low frequency asymptote and also a high frequency asymptote. So, as omega approaches 0, H1 approaches 1 over minus 3 plus 4 j, or in decibels this is essentially 20 log to base 10, 1 over 3 square plus 4 square, the whole thing under square root. So, once again the low frequency asymptote comes out as a constant, and when I calculate this value, essentially what I get is minus 13.98 decibels. And as omega approaches a very large number or infinity, H1 approaches 1 over omega j. So, in decibels essentially I get 20 log of 1 over omega, which is essentially minus 20 log of omega. So, once again we see that the low frequency asymptote is essentially will be represented by a constant horizontal line, which is 13.98 decibels away, negative 13.98 decibels away from the horizontal axis, and the high frequency asymptote will be a straight line, but it will have a negative slope of minus 20 decibels per decade. Let us do the same thing for H3 j omega. So, the relationship is minus 3 plus omega minus 4 times j. So, as omega approaches 0, so excuse me, so earlier I had written H1, this should be H2. So, as omega approaches 0, H3 approaches 1 over minus 3 minus 4 j, or in decibels again it is 20 log 10, 1 over 3 square plus 4 square, whole thing under square root, and that is again minus 13.98 decibels. And as omega approaches infinity, H3 approaches 1 over omega. So, in terms of decibels I get 20 log to the base 10, 1 over omega, which is minus 20 logarithm of omega. So, essentially what we are seeing here is that the magnitude part for H2 and H3, they are same. The low frequency asymptote for the magnitude of H2 is minus 13.98 decibels, constant line, and same thing for H3, and the high frequency asymptote for H2 is essentially a negative sloped line with a slope of minus 20 decibels per decade, and it is the same thing for H3. So, if I have to construct a Bode magnitude plot for H2, on the horizontal axis I am going to plot log of omega, on the vertical axis I am going to plot in decibels. My horizontal, so my low frequency asymptote, so let us say I am plotting for, I am doing a Bode magnitude plot for H2 and H3 because they are the same. So, my low frequency asymptote is again once again a horizontal straight line. My high frequency asymptote is a negatively sloped line, and the slope of this is minus 20 decibels per decade, and the crossover point is corresponds to this point, and this number is such that when omega equals 3, the crossover point is 0.2. So, when omega equals 0.2, then low frequency asymptote and the high frequency asymptote, after the crossover point, the high frequency asymptote becomes more important. So, this is log of 0.2. So, this plot is for H2 as well as H3. Now, what I am going to do is I am going to develop a Bode plot, magnitude plot, H2. So, it is not H2 and H3, but rather I will develop a plot for H2 plus H3. So, essentially I will add these two lines. So, my low frequency asymptote will be once again a constant line. It will be a constant line such that the y intercept will be negative 13.98 times 2 decibels. So, this is my low frequency asymptote, and that is minus 27.96 decibels. On the horizontal axis, I am plotting log of omega. On the vertical axis, I am plotting decibels. Low frequency asymptote once again is minus 13.98 times 2, which is negative 27.96. The high frequency asymptote is a steeply sloped line, and the slope is negative 20 plus negative 20 decibels per decade. So, the overall slope is minus 40 decibels per decade, and once again the crossover point remains as is and it does not change when I am just adding up the Bode plots for H2 and H3. So, when I am summing up the Bode plots for H2 and H3, as I mentioned just now, the crossover point still remains omega being equal to 0.2, which means on the horizontal axis it gets plotted as log of 10 of 0.2. So, this is this plot is a combination, is a Bode magnitude plot for a combination of two functions or a product of two functions, which are H2 and H3. So, now we will construct the final Bode magnitude plot, which will be essentially a sum of 3 individual magnitude plots for H1, H2 and H3. Once I sum all these 3 up, I get the Bode magnitude plot for function H1 times H2 times H3, which is same as the original H, the transfer functions which we had developed. So, for purposes of clarity, I will just redraw the magnitude plot for H2 times H3. So, the low frequency asymptote is a horizontal line with the y intercept at minus 27.96 dB, and this low frequency asymptote dominates the response of the system represented by H2 times H3 up to a specific crossover point, which is which corresponds to this point when omega is larger than 0.2, then the high frequency asymptote starts dominating the response. So, that is my crossover point, and after that I have my high frequency asymptote, and here the slope is minus 40 decibels per decade. This is mag plot, actually I will be more specific, Bode magnitude plot for H2 plus H3. And then we had constructed a Bode magnitude plot for H1 and that was the low frequency asymptote was again a horizontal line with a y intercept of 6.02 decibels. The crossover point was omega equals 2 and after the crossover point high frequency response starts dominating, and that is represented by a straight positively sloped line, the slope being plus 20 decibels per decade. So, now I am going to construct a Bode magnitude plot So, just to be mathematically consistent, this is a Bode magnitude plot for a function which is equal to H2 times H3, not H2 times, not H2 plus H3, but rather H2 times H3. So, now we will construct a Bode magnitude plot for AHS, which is our original transfer function when S equals j omega, and that is nothing but a product of three individual transfer functions H1 j omega times H2 j omega times H3 j omega. And the way we are going to do it is, we are going to add these two plots. We add these two plots and we get our final answer. So, that is how I am going to construct it, and this is how the final plot looks like. Once again, my horizontal axis is a logarithmic axis where I am plotting omega. On the vertical axis I am plotting decibels. So, what we see here is that up to omega equals 0.2, the response curves are essentially straight lines. So, let us say this is log of 0.2, this is log of 2, and up to this point I just add two horizontal lines. One line is plus 6.02 decibels away from the x axis, the other line is minus 27.96 decibels away from the x axis. So, my first segment of the line will be something like this, and this is minus 21.94. Now, how did I get this 21.94? Essentially, it is minus 27.96, which is this number, plus 6.02 equals minus 21.94 decibels. So, the response curve for a system which is represented by this transfer function H is essentially a constant horizontal line which is minus 21.94 decibels away from the horizontal axis up to a frequency of 0.2, angular frequency of 0.2. Now, after that I have another segment of frequency, another band of the frequency which is from 0.2 to 2. And for this region we see that this particular transfer function, it is having a slope of negative 40 decibels per decade, while this transfer function is still in the constant range. So, because this is let us say log of 10 of 0.2. So, the overall transfer function will be a negatively sloped line. It will be a negatively sloped line, and the slope and the slope will be minus 40 decibels per decade up to angular frequency of 2. Once I have exceeded the angular frequency of 2, then this part of the curve for H1 also starts to kick in. So, my overall slope becomes minus 40 plus 20 decibels per decade. So, my slope becomes lesser, and here the slope is minus 20 decibels per decade. So, this is my overall Bode magnitude plot for a transfer function h of j omega, where h of j omega is essentially a product of 3 individual transfer functions h1 times h2 times h3. So, we will use a very similar approach for also developing a Bode phase plot for this complex transfer function h, and that is what we are going to do in next several minutes. So, now our objective is to develop a Bode phase plot, for h of j omega. So, once again my h, where h of j omega is a product of h1 j omega times h2 j omega times h3 of j omega. And once again, for purposes of clarity, I am going to rewrite the functions for h1. It is 2 plus j omega. For h2, it is 1 over minus 3 plus 4 plus omega times j, and for h3 it is 1 over minus 3 plus omega minus 4 j. So, the phase of all these specific individual functions will be something like this. For h1, phase will be tan inverse of omega over 2. For h2, the phase will be negative because it is in the denominator of tan inverse of omega plus 4 over 3. Actually, in the denominator I will have negative 3, and for h3 it will be negative of tan inverse omega minus 4 over minus 3. So, these are the 3 different relations for phase for each particular sub transfer function. Now, we will start constructing Bode phase plots for each of these transfer functions, and then finally, we will just add them up and we will get our final Bode phase plot. So, for h1, when omega goes to 0, phase of h1 goes to 0, when omega goes to infinity, phase of H1 goes to pi over 2. So, my Bode plot is going to look like, for low frequency it is a constant line at 0. So, once again let me just label the axis. Horizontal axis is log of omega, vertical axis is phase, and this is in radians. So, this is my low frequency asymptote, and my high frequency asymptote is going to look like this, and the crossover point where the intercept is going to be pi over 2. This is 0, and my crossover point is log of 2. So, now I am going to do same thing for H2. As omega is approaching 0, phase of H2 is approaching negative of tan inverse of 4 over minus 3, and that is 0.93. I'll be a little more precise, 9287 radians. And as omega is approaching infinity, phase of H2 is approaching negative of tan inverse omega over minus 3, and when omega becomes extremely large, then essentially it becomes plus minus pi over 2. So, when omega has a positive value and it is extremely large, then it becomes pi over 2. I will again, so the Bode plot for this H2, the phase plot for this will look like something like this. So, again I am having phase of H2 being plotted here on y axis. On the horizontal axis I am plotting log of omega in base 10, and this is my low frequency asymptote. The crossover point is log of 0.2, and my high frequency asymptote is once again a constant line, and the value y intercept is pi over 2. For H3, as omega approaches 0, phase of H3 approaches minus tan inverse minus 4 over minus 3, and that is essentially minus 0.9287. And as omega approaches infinity from the positive side, then H3 phase approaches negative of tan inverse omega over negative 3, and that is pi over 2. So, just for purposes of clarity, let me just label this. This is phase plot for H1, this is phase plot for H2, and now I am going to construct a phase plot for H3. So, my low frequency asymptote is again a horizontal line with a y intercept of minus 0.9287. Once again I am plotting here phase, and here I am plotting log of 10 of omega. So, my low frequency asymptote for phase is a horizontal line with a y intercept of minus 0.9287. Then after the crossover point, which corresponds to omega being equal to 2, I have a high frequency asymptote, and the high frequency asymptote also has a y intercept of pi over tau, and once again this crossover point is log 10 of 0.2. So, this is H3. I am plotting phase plots. So, I have plotted phase plots for H1, H2 and H3 on a log scale. So, my next logical step is just to add these 3 up, because we know that if there is a function which is a product of 3 individual functions, then the phase for this complex function is nothing but a sum of phases of each individual subfunction. So, once I do this exercise, my final curve it looks like this. On the horizontal axis I am plotting log of omega, on the vertical axis I am plotting phase of the original transfer function, and I know that for the range 0 to 0.2, the contribution of H1 and H2 cancel each other, and the contribution from H1 is identically 0. So, for the range 0 to 0.2, my curve for the phase is a horizontal line which is exactly cutting the vertical axis at 0. Then for the range 0.2 to 2, the contribution from H1 is pi over 2, no excuse me, the contribution from. So, for the range of frequencies or angular frequencies between 0 and 0.2, we have seen that the phase plot is essentially coincident with the horizontal axis, and the x and the y intercept is 0 radians. So, this is what it corresponds to, this dark blue curve. For the angular frequency range from 0.2 to 2, the contribution from H2 and H3 is pi over 2 radians. We see it from here. Contribution from H2 and H3 is pi over 2 radians, while contribution from H1 still remains 0, because the low frequency asymptote for H1 is 0 up to 2 radians per second. So, what that means is that for this range, my phase curve will once again be a constant line, but it will be a constant line. However, the y intercept will be at pi radians, right. Then for the range, so this is, excuse me, then for the range where angular frequency exceeds 2, which is for this range, let us look at the contributions from H1. From H1 the contribution is pi over 2, for H2 the contribution is pi over 3, again a constant, and for from H3 the contribution is once again pi over 2. So, pi over 2 times pi over 2, pi over 2 plus pi over 2 plus pi over 2 is 3 pi over 2. So, for this range the phase response is 3 pi over 2. So, once again I have a horizontal line and it extends to infinity, and that is my phase response curve, my phase curve, Bode phase curve for a transfer function, which is again a product of 3 individual transfer functions H1, H2 and H3. Now, bear in mind that this is the asymptotic response curve. However, in real systems, the transitions from this range to this range to this range, they are more or less fairly smooth. So, the actual response curve will be bounded by this asymptotic response curve, but however, this asymptotic response curve, it gives us some qualitative understanding how the system is going to behave. The actual curve in this case may very well look like something like this, and that is what I am going to plot in light blue. So, at extremely low frequencies, it is bounded by this dark blue line curve, which is essentially a horizontal line cutting the vertical axis at 0. At extremely high frequencies, it is bound by another horizontal line, which has a y intercept of 3 pi over 2. So, this is how we can construct Bode magnitude plots and Bode phase plots for transfer functions, which can be broken up into individual poles and zeros, and once we have an individual curve for every single pole and every single zero, then all we have to do is we have to add these up and we get a Bode magnitude plot, and we also get a Bode phase plot for the original transfer function, which could be a combination of several individual pole and zero related transfer functions. So, that is pretty much what I wanted to cover in terms of Bode plots, and I think this introduction will help you develop Bode plots for magnitude and phase for fairly complex transfer functions, and that will come in really handy once we start talking about acoustics in detail. So, we have covered a slew of topics: complex algebra, complex numbers, Bode and Bode magnitude plots, Bode phase plots, pole zero plots, and so on and so forth. And all these concepts will come in fairly handy once we start talking about acoustics in detail. So, having said that, now I will move to the wave equation, which is the first concept we are going to talk about in context of this course on acoustics. So, before I start talking about the wave equation per se, just wanted to give you a brief understanding of what this equation means and what is it that we are trying to do through the wave equation. So, as we had talked about earlier, in acoustics we can break up this whole range of issues and problems which we try to solve in the area of acoustics into 3 groups. The first group relates to a situation where noise or sound is being produced. So, you have a source and this source produces sound, and then I have a listener, and this sound, and this listener could be a human being, an animal, a microphone, or whatever. So, I have a source, I have a listener, and I have a medium. And there are different branches of acoustics which deal with these three things. There is a branch which helps us understand how sound is generated, and a lot of that information comes from ideas in electroacoustics. So, electroacoustics along with some related areas of acoustics, they help us understand how the sound gets generated. Then in terms of listening or recording sound or analyzing sound or sensing sound, here we deal with two broad areas. One is electroacoustics, electroacoustics helps us design, for instance, microphones which help us sense sound, and then that can be recorded. And then another very big area is psychoacoustics. And what psychoacoustics helps us do is, it helps us understand sound from the standpoint of the human individual. So, it is one thing to record data and see it on a computer screen, but how does brain understand sound and how does brain interpret sound signals? That is what acoustics helps us understand. So, this is about sound generation. This whole area is about sound, sensing of sound and interpreting of sound. And as sound travels from the source to the listener through a medium, the branch of acoustics which deals with this propagation of sound is called physical acoustics. So, that is physical acoustics. So, sound gets generated, and there we seek the help of electroacoustics to understand that phenomena. It gets propagated from point A to point B, and there we seek the help of physical acoustics to understand that propagation phenomena. And then finally, there is a listener who is listening to sound, and there the understanding is derived through principles of, once again, electroacoustics and or psychoacoustics. So, wave equation is it helps us understand how sound gets transmitted through a medium. So, that comes in the realm of physical acoustics. So, that is a very broad context in which I wanted to place wave equation. Where does wave equation fit in the overall scheme of things? So, what we will be doing in this course is that first, now starting from today onwards, we will do several lectures on physical acoustics, and then we will try to understand how sound gets propagated through a medium. Once we have done that, then we will move on to electroacoustics, and there we will try to understand how we can generate sound. So, we will address this part, and then finally, we will go to the listener, and there we will try to understand how sound gets recorded, interpreted, and so on and so forth. So, that is the overall course landscape, and that is the context where we can place wave equation. So, what we are going to talk about is wave equation. And once again, what this equation helps us do is helps us understand how does sound get propagated as it travels through a medium. Now, this medium could be a piece of solid, as in a piece of steel, or it could be a volume of gas. So, most of the times when we speak, we are sitting in air, and sound gets propagated from our mouth to an individual's ear. So, that is again where wave equation comes in handy, and there are different versions of wave equation for different types of medium, or it could be the case of a fluid, not to be more specific, the case of a liquid, where you have sound getting propagated in water through miles and miles or kilometers and kilometers of distances, and how does get sound propagated there in that type of a medium. So, in each of these different media types, it is the wave equation which helps us understand how sound gets propagated. What we are going to talk about today is specifically propagation of sound in elastic media, and more specifically in air, at atmospheric conditions. And even more specifically, we will talk about the 1D wave equation. So, a typical example of 1D wave equation could be, I have a long tube and I am speaking in that tube, and the tube may be bent, but sound travels through that tube, through the air inside the tube, and it can be heard at the other end of the tube. So, that is a typical example of 1D wave equation. Another example could be again a rectangular pipe or a channel. Let us say you have a HVAC duct. At one end of the duct you have a blower which is blowing air into the duct, and in that process it is also generating some noise, and that noise moves through the duct, and once sound comes out from the duct into an air conditioned room, that sound gets heard. So, what is the phenomena and how is that propagation happening through the duct? That is something 1D wave equation will help us understand. So, what we will be talking about is wave equation in one dimension. Now, initially we will start this discussion by having propagation of the wave in one dimension, where my coordinate system is a rectangular Cartesian coordinate system, but later I will use mathematics to also explain the wave equation in a radial or a spherical coordinate system. So, let us consider a 1D piece of air, one dimensional piece of air, where sound is getting propagated, and let us say the initial pressure and initial pressure, initial density, initial volume and initial velocity of this air are P naught, rho naught, V naught and U naught. And then because of the disturbance due to sound propagation, these values change. So, the initial values have a subscript of 0 and the final values have a subscript of P t. So, my P t, which is the final pressure, and it can depend on x, which is the position. So, again it is not x, y and z, but it is just x because it is only in one dimension. So, my final pressure, which is P t, is dependent on x and it is also dependent on time. So, that is equal to P 0, which is my initial pressure, which was again dependent on x and t, it was P 0 plus some disturbance which is dependent on x and t. So, once again here I am saying essentially that P 0 does not change with time and x, because it corresponds to standard atmospheric pressure, which is approximately 10 to the power of 5 newtons per square meter. So, that is the relation for pressure. Likewise, the density of the air under consideration, the final density could be rho subscript T, and that is equal to my initial density, which is rho naught, plus incremental change in the density, which is rho, which is again a function of position and time. So, that is my relation for density. Then my volume of air, let us say my final volume of air is V subscript T, and that is equal to initial volume V 0 plus increment some change in volume, which is tau, again a function of position and time. So, that is the relation for volume. And finally, I have a relation for velocity, velocity being u. So, my final velocity is u t, which is equal to an initial velocity u naught plus some change term, which is represented by u, which is again a function of position and time. Now, usually u naught is essentially 0, because we assume that in the initial state of affairs there is no motion in air. So, u naught is 0. So, I can drop this term, because u naught is 0 usually. Also, it is important to provide some values at this point of time. So, my P naught equals approximately 10 to the power of 5 newtons per square meter. My rho naught, which is the density of air at MSL, is 1.18 kgs per square meter, and volume could be, initial volume could be variable, because I can take as much, I can consider as much volume as I want. So, once again P naught, rho naught, V naught and U naught, which is 0 in this case, they are my initial pressure, values of pressure, density and volume and velocity, while P, rho, tau and U are my incremental values for pressure, density, volume and velocity. And when I add these two up, the initial value and the incremental value, I get final values which are designated by a subscript T. So, this is how I am going to frame my problem. So, what I am interested in knowing is how are P, rho, tau, U all interrelated, and as I am trying to develop these relationships, I will make two very important assumptions. So, I will make two important assumptions. The first assumption is that this is a one dimensional system, and so my system is one dimensional. and what that means is that del over del y, that is the partial derivative of any variable with respect to y, is equal to 0, and del over del z is also equal to 0. Second assumption I am going to make is that I have constant mass particles. So, I have a piece of air which has initial mass, its mass is not changing as it moves through the system. So, essentially what that means is rho t v t is same as rho naught plus rho times v naught plus tau, and that is same as rho naught v naught plus incremental terms, and that is equal to rho naught v naught. So, these are the two key assumptions, and then we will also talk a little bit more about some other assumptions in the next class, but this is how I am going to frame my problem. And in the next class what we will do is we will try to develop an equation of how pressure and density and velocity and all these variables are interrelated through three important equations. One is the Newton's equation, which is an equation for force equilibrium. So, if I have a piece of fluid, it has to have equilibrium from using Newton's laws of motion. The second equation I am going to use, or relationship I am going to use, is that for conservation of mass, and that is what I call continuity equation. And finally, I will use a relationship which links pressure and volume through a material constitutive equation, and through these three equations, equation of momentum, that is Newton's law, equation of mass conservation, and material constitutive equation, I will develop wave equation in one dimension. Thank you very much.